ARISSat got its name from the ARISS organization, which means Amateur Radio on the International Space Station. And this ARISSat project is a group project between AMSAT, who's building the satellite, NASA, who is helping facilitate getting the satellite to Russia, and Russia, which is paying for the upmass and the battery. But then there are also partners in the UK and Europe and Japan and Canada that are all part of this amateur radio group, ARISS, that is sponsoring all this.
Okay, we're at the Dayton Hamvention at the AMSAT booth with Gould Smith, WA4SXM, and I want to ask Gould to tell us a little bit about this satellite here. Gould, give us a little rundown on what you've got here.
All right, what we have here is a satellite that originally was designed to be placed, electronic parts to be placed inside one of the Russian Orlan spacesuits. Last July we lost the spacesuit, and so we had to quickly come up with some kind of superstructure to house our electronics. As you can see in this particular diagram, there are going to be solar panels on all 6 sides of the structure, and so the shape of the superstructure was dependent upon fitting the 6 solar panels. So that determined the shape that we came with. And on the top and bottom, that gave us half an opening to put the external electronics and switches and entrance plates.
Okay.
So this is a aluminum frame with horizontal and vertical cross pieces, very strong aluminum corner pieces, to which we have handles on all 4 corners, but they also are the main structural integrity of the satellite. There are solid metal plates on the top and bottom with screws 1.5 inches or so apart to give it great structural stability. The solar panels are going to go on a aluminum plate with a carbon fiber back plate, and then the solar cells on top of that. There'll be Velcro that attaches the carbon fiber plate to the aluminum plate because there was a temperature coefficient problem, and we're going to be seeing temperatures from +40 to -35 degrees C. And when we tested that, the solar panel deformed. So we're using the Velcro, which will absorb 4 to 5 millimeters. We only expect a millimeter difference, but it'll absorb that, and so that's a reasonable, quick, inexpensive solution. Okay. This is the band pan for ARISSat. We're going to have 4 types of transmissions. We're going to have an FM transmission, a CW transmission, a transponder transmission, and a BPSK transmission modulation. The FM signal will contain voice ID. It will contain spoken telemetry values, slow scan images taken by the cameras, and international greetings from children around the world in 16 different languages and 27 different messages. The CW signal will send out some telemetry values in CW, and also a list of amateur radio call signs for people that have been instrumental in the ARISS program. The BPSK will be a sideband transmission that will be at 1K rate and will contain the telemetry data, the full telemetry data, and also the Russian experiment data. And it will be a telemetry packet, 1 of 5 Russian experiment packets, telemetry packet 2 of 5, and do that round the clock. So in an average 8-minute pass, you should easily be able to copy a number of telemetry frames, and they're about 13 seconds each. So you'll be able to copy all the Russian experiment data, and it's a good amount of telemetry data. The fact that all this downlink data will be able to be put on the internet and sent to a worldwide available repository. People can watch real-time telemetry or go back and get stored data at any time. The other module over here is the MPPT, which is Max PowerPoint Tracker. And these modules, each one connects to 3 solar panels. And they actually take whatever energy is produced in the solar panels, combine it, and charge the battery and help run the satellite. And that's set up so that if the satellite's in sun, they should be plenty of energy to run the satellite and also charge the battery.
And these are LEOs, right?
Pardon?
These are LEO satellites, low Earth orbit?
Yes, this is going to be in a very low Earth orbit. It's going to be released from the International Space Station and in a backward, downward trajectory and actually spiral into the Earth in 8 to 12 months.
So that'll be the lifetime.
That'll be, well, and it'll be the lifetime before it gets too hot or the battery expires, or, I mean, we don't know what's going to happen first.
So how many of these are planned?
This is a prototype. We already have 4 structures. We're building 4 structures this month. We're sending 2 to Russia. One is a flight unit, another is a backup unit. We only have 1 set of solar panels. So the other 2 we'll have in the United States are ready to fly, and we can take the components out and put them into a suit if it becomes available. But we also have all the components in the superstructure, so we'll have 2 satellites ready to. Okay. This is the RF module that contains a receiving module and a transmit module and a command receiver module in here. So it takes the output from the 10.7 IF from the IHU or the SDX in the IHU module, and this particular one has a 2-meter transmitter and a 70-centimeter receiver. But the beauty of this modular system is that you can put any transmit receiver pair out here with a 10.7 IF input or output, and you've changed the transmit and receive frequencies. This in the center, this large box, is the IHU module that contains 4 units. There's a backplane or an ICB interconnect board that connects all the 4 boards. There's a power supply board that takes the power from the solar panels and the battery and breaks it down into 4 other voltages and supplies the system. Then there's the IHU, which is the integrated housekeeping unit. That's actually the computer or the main controller of the system. And the 4th board is the SDX, or software transponder board, software defined transponder. It takes an analog input from the, it takes an analog input from the receiver to do the transponder, and it takes a digital input from the IHU and generates analog output from the digital input signal, because it's all software that converts this analog and digital back into an analog signal. And that's how we're able to have
All
right. ARISSat got its name from the ARISS organization, which means amateur radio on the International Space Station. And this ARISSat project is a group project between AMSAT, who's building the satellite,